So we're going to have a look at the last topic in your notes, which is group 2 elements and their compounds, which starts on page 92. The unfortunate thing about this topic is, whilst most topics in AS chemistry are actually quite interesting, this unfortunately is not one of them. It's almost as if the examiners went out of their way to try and design a topic that was as boring as possible. Now, the one good trade-off of that is it's not actually the most hard topic you'll come across. It's essentially a lot of learning of some trends and some definitions. So we'll dive straight into it. So obviously this topic is about the group 2 elements and their compounds. So magnesium all the way down to, beryllium, magnesium all the way down to barium. We start with a kind of analysis of the elements themselves and see if we can get some trends about how they behave. So first to introduce, group 2 elements are regarded as S-block elements. Outer shell electrons are in an S subshell. We'll come back to that. Comparison to group 1 metals, they're a bit harder, a bit denser. They're actually not quite as reactive as group 1 metals. And in air, the surface of the metal is covered with an oxide layer, so generally they will appear quite dull, which you know from looking at magnesium, which you've used quite a lot throughout your time in school. First little thing is a little analysis of the electron configurations. Obviously that's good revision. Again, to bring up the fact that electronic configurations are definitely an AS1 topic, but definitely can be brought up in AS2. They're allowed to bring across wee bits and pieces of the course like that. So they could ask you for configurations of these elements. So if you want to have a go at that yourself, there's the elements, pause video now, otherwise I'll just go through them. And again, remember you can use your periodic table and the positions of elements to guide you with that. But I'll just jot down the answers here. So beryllium is 1s2, 2s2. Magnesium, 1s2, 2s2, 2p6, 3s2. Calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Strontium, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 5s2. So remember that even though the 4s fills up before the 3d, we always put the 3d first numerically. Now for the final two, we're getting quite big here, so it says at the top here you should use noble gas configurations, because eventually we're going to go into like the F block here, which is quite hard to do. So barium is just 2 after xenon, so we just put xenon in square brackets, and then we know it's 6s2 after that. And then radium is 2 after radon, which gives you 7s2. So the electronic configurations are one thing. There is clearly a wee trend to spot here, which is at the end of their configurations. They all end with electrons, the outer electrons, being in an s orbital. 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. So a very common question would be, why are these elements a member of the S block? Again, that's the definition you've come across before. S block means the outer electrons are found in an S subshell, which we've proved to be true by looking at all their configurations there. So that, technically speaking, is a trend. So on this page we've got the trend section. There's 3 you're meant to know about: electron configurations, atomic radius, and first ionization energy. We've kind of already covered the first trend. The atoms of group 2 elements all have electronic configurations ending in s2. As you go down the group, the outer electrons occupy a higher principal energy level. So it's not really much to say about that, but just the fact that they all do end in s2, and that's a comparison. As you go down, you will get more and more subshells being filled up. We saw that here. You're adding orbitals, you're adding principal energy levels as you go down that group. The first maybe proper trend would be in the atomic radius. Now, that's not really something we've looked at too much this year, but the clue's in the name. It's basically an idea of the radius of your atom, in other words, how big your atom is. In this complicating looking table, we don't need to worry too much about it. It gives you a comparison of the radiuses of the group 1 metals and their ions, the group 2 metals and their ions. So we'll focus on the group 2 metals. Hopefully you can see just by the numbers and even the pictures as well, they're definitely getting bigger as you proceed down the group from beryllium all the way down to barium. The justification for that isn't too tricky. First of all, point atomic and ionic radii increase down the group due to the addition of, well, essentially you're adding more filled inner shells. As you're going down each element in the group 2, you're going to a new principal energy level. New principal energy level means you've got a filled inner shell and you're starting to layer up those filled inner shells. So due to the addition of filled inner shells, and this means the outer shell electrons are further from the nucleus. Little comparison about group 1 versus group 2, obviously they're very similarly reacting metals. The group 1 atoms and ions are actually larger than group 2, which is quite like a subtle effect. It's to do basically with the charges on those. If we compare two beside each other, we'll go right at the top here, lithium and beryllium. So lithium is in group 1 and beryllium is in group 2. If you think about the kind of structure of lithium beryllium atomically, beryllium's got one more proton than lithium does. Essentially, it's got a more charged nucleus. If you might remember from your trends in ionization energies, as you go across a period, you have more protons, you increase the nuclear charge. So there's a bigger nuclear charge on beryllium than there is in lithium. If you think about the electrons being in their orbitals buzzing around, the lithium nucleus will pull those electrons towards itself. But the key thing about beryllium, whilst it's still the same number of principal energy levels, because you've got the increased nuclear charge, it will start pulling a wee bit more than lithium will. And that will actually cause the electrons to contract and the size of your atom to decrease a wee bit. So your group 2 metals tend to be a wee bit smaller than your group 1 metals just because there's a higher nuclear charge on those particular atoms, which pulls all the layers of electrons towards themselves and makes it a bit smaller. The final trend you have to know about is about the first ionization energy, and again that goes back to something he did in AS1, which were at the very start, ionization energies. As a quick reminder of what ionization energies are, it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions with a positive charge. Putting that in equation form, if we put beryllium again, beryllium as gaseous atoms, 1 mole would be going to beryllium plus, with 1 mole of electrons being given off there. So it's the energy to take away the outer electron in each case. If we remind ourselves of the key trends we used at the time when we looked at ionization energies, you hopefully remember that these 3 things were quite important. We looked a lot at the idea of nuclear charge. We looked at the idea of distance. And we looked at the idea of shielding. And those will still be important for looking at this trend in ionization energies. Now, we have looked at the trend in first ionization energies down a group before, and it's no different for the group 2 metals, just more of a one in context. The first and second ionization energies decrease down the group. We'll not worry too much about the second one just for now, just the first one. Like the atoms of alkali metals, the group 2 atoms change in 2 ways on the group. The charge on the nucleus increases and the number of inner full shells also increases. So you kind of got 2 competing trends here. So let's go down the bottom and sort of sketch it out. I'm going to compare ones from the top and the bottom. Let's look at beryllium, quite a small one. Let's look at barium. If you look at your periodic table, look at your atomic numbers, you'll be able to work out the number of protons that beryllium and barium have. Beryllium's got an atomic number of 4, so it's got 4 protons. Barium's got an atomic number of 56, so it's got actually a huge number of protons. If you just looked at that by itself, that would give you a much higher nuclear charge for barium because there's so many more positive charges in the nucleus. That would lead you to believe that barium should hold on to its electrons quite tightly, which means it'd be quite hard to remove the electrons, which give it quite a high first ionization energy. We don't see that. We've looked at the trend here. The ionization energies decrease down the group. So there must be some competing explanation, which means that barium actually gives up its electrons quite easily. The competing thing is just the size of them. Beryllium is quite a small atom. It's in the second period. Barium is quite a big atom. It's got lots of filled inner shells. So whilst barium's got loads of protons in the nucleus holding electrons in, the outer electrons are actually really, really far away from the nucleus compared to beryllium, where it's quite small. Because remember, first ionization energy is just taking that outer electron, or one of them, and removing it. And however easy that is what the first ionization energy will be. So in this case, while you've got a high nuclear charge, you've got a low distance or small distance from that electron to the nucleus, the outer electron to the nucleus. You also don't have much shielding. Remember, shielding comes from the number of filled inner shells, and there's not many filled inner shells here. Whereas with barium, whilst you have got a very high nuclear charge, you have got a very large distance between that nuclear charge and the outer electron being removed. And you also have a massive amount of shielding from all of those filled inner shells. So that kind of overtakes the fact that you've got a high nuclear charge. These two factors become much more important, which means as you go down the grip, from beryllium all the way down to barium, you will actually have a decrease in your first ionization energy. So just building on that within the blurb here in the paragraphs, the shielding effect of the inner electrons means that the effective nuclear charge attracting the outer electron is always 2+. Don't worry too much about that. It's basically saying because you've got all these electrons in barium, it's not actually 56+. It's the same as across all of the group 2 metals. It evens out to being a 2+ charge. Down the group, the outer s electrons get further and further away from the same effective nuclear charge, so they're held less strongly and the ionization energy decreases. Similarly, the number of filled inner shells increases down the grip, which causes increase in shielding, contributing to the first ionization energy decreasing down the grip. Now, you can make that quite concise. Essentially, the things bring up are things we've talked about in this 3 diagram. So whilst the nuclear charge is bigger in barium, there's much more shielding and a much larger distance between the barium nucleus and the outer electron, which means it's easier to remove the outer electron, which means the ionization energy is smaller. Little kind of side point here about your third ionization energy. If you remember about being group 2, it's quite easy to form that 2+ charge, but you wouldn't really form a 3+ charge. It would involve moving electrons from a lower energy level, which would be quite hard. So to remove a third electron to form a 3+ ion takes much more energy, because the third electron has to be removed against the attraction of a much larger effective nuclear charge. It means it's never feasible to form 3+ ions, as you might expect. The implication of this all is, if you bear in mind what most reactions involve, it's loss or gain of electrons, and metals always lose electrons. If it is actually easier to remove electrons on the grip because the ionization energy is lower, those metals will actually become more reactive as you go down the grip. So that's the implication of it being easier to remove these electrons. If we compare, barium will be much more reactive than beryllium will at the top.